Alright, so they want us to take a look at the following triangle. It says each number is the sum of two numbers diagonally above. If there's not a second number, think of it as 0. So what they did is they understood as 0 to be right here. So 0 plus 1 gave us 1. Again, 0 plus 1, or 1 plus 0 gave us 1. 1 plus 1 gave us 2. There was no number on either side, so we think of it as 0. 0 plus 1 is 1. 1 plus 0 is 1. Basically, you take this whole triangle, and there's going to be ones down both sides of this triangle. 1 plus 2 gave us 3. 2 plus 1 is 3. We added our ones to the outside. So if you want to start by adding your 1 to the outside, you can do that. And then we got 1 plus 3 is 4. 3 plus 3 gave us 6. And 3 plus 1 gave us 4. And then we know that we have to add a 1 to that outside of that triangle. We're going to keep doing the same thing all the way down. So we add a 1 to the outside. 1 plus 4 gives us 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5 to give us a 1 on the outside. Now they want us to write the numbers of the next 3 rows. So I know I'm going to start with a 1, correct? What's 1 plus 5? 6. Then we have 5 plus 10, which is 15. 10 plus 10, 20. 10 plus 5, 15. 5 plus 1, 6. And then what do we add to the end? A 1. So that's the first of the next 3 rows. Pretty simple, right? Alright, we add a 1 to the outside of this. 1 plus 6 is 7. 6 plus 15 is 21. 15 plus 20 is 35. 20 plus 15 is 35. 6 plus 1 is 7, and then we add a 1 to the outside. Last row that they want us to do. This could keep going on forever. 7 plus 21 is 28. 21 plus 35 is, what is that, 56? 70, 56, 28, 8, and 1. Then they ask us what patterns do we notice. Well, I've kind of already pointed one out to you. First row is all ones, right? First column, our first diagonal row. Then we've got 1, 2, 3, 4, 5, and then we got 6, 7, 8, right? Keep going. From 1 to 3, I add 2. 3 to 6, I add 3. 6 to 10, I add 4. 10 to 15, I add 5. 15 to 21, I add 6. 21 to 28, I add 7. So the next I would probably add 8. This one would be 3 to 6. Oh, wait, I skipped a row. No, I didn't. 3 to 6 to, what was that, 10? I don't guess there's really a pattern right there. So we just kind of discussed those patterns. We're not going to write any that we actually see. Then it says create a formula for the sum of numbers in the nth row of the triangle. So let's add this first row up. Well, that's only 1, right? So I'm just going to write a 1 down here. And what I think is the second row, 1 plus 1 gives me 2. 1 plus 2 plus 1 is 4. Then I've got 1 plus 3, which is 4, plus 3 is 7, plus 1 is 8. It's 5 plus 6, which is 11, plus 4 is 15, and then plus 1 is 16. Starting to get into some numbers that are That's 20, 32, I think. 1 plus 5 plus 10 plus 10 plus 5 plus 1 is 32. 1 plus 6 plus 15 plus 20 plus 15 plus 6 plus 1 gives me 64. Next, I got 1 plus 7 plus 21 plus 35 plus 35 plus 21 plus 7 plus 1. That's 128. And then my last row that I have is 1 plus 8 plus 28 plus 56 plus 70 plus 56 plus 28 plus 8 plus 1. It's 256. They wanted us to come up with some sort of equation for this. So the equation I came up with was 2 to the n power. Well, 2 to the n power. If we say that our equation is 2 to the n power, this has to be row 0 because anything to the 0 power is 1. So this would be row 1, row 2, row 3, row 4, row 5, row 6, row 7, and row 8. Like I said, it doesn't necessarily stop at row 8. That is just where they asked us to stop today. Everybody got it for me? Alright, now let's go to our next page. We're going to skip example 1. So I put a big X through it. And then I want you to just kind of see where I'm getting this from. Let me go back to my Schoology. Alright, actually before example 1 in your textbook, they give us all sorts of formulas. And so what I'm going to have us do together is I'm going to have us write our formulas down in the margin. And just so you see where I'm getting these from, I was going to pull this up to show you. Let's see if it'll let me pull it up right here. So if you were at home doing this, you would see all of these formulas. They got difference of squares, square of sums, difference of cubes, and sum of cubes. So I'm going to start by writing these in the margin of example 1. So we'll start with difference of squares. Alright, so the difference of squares says if we've got a squared minus b squared, that is equal to a minus b times a plus b. Or I could write it as a plus b times a minus b. Either one would be correct, okay? Next we have square of a sum. So that's a plus b squared, which they say is a squared plus 2 times a times b plus b squared. Next, I've got the difference of cubes. So that's if we've got a cubed minus b cubed. We say that that is equal to a minus b times a squared plus ab plus b squared. And then last, we've got sum of cubes. So that's a cubed plus b cubed, and our formula for that would be a plus b times a squared minus a times b plus b squared. And then we're going to work one of the examples that they give us in the book, which is 2x squared plus y cubed squared. Alright, so this looks like it is the square of sums because of the addition sign in between, and it's raised to the second power. So we're going to use this formula here to simplify it. So we know a is 2x squared, so we're going to take 2x squared, raise it to the second power, plus 2 times a, and b is y cubed, so times b, plus b squared. And then we simplify it. Two squared is 4. Anytime you've got two exponents, x squared raised to the second power, you multiply. Anytime you've got two exponents that are you got an exponent raised to another power, you multiply it. Plus 2 times 2 is 4 times x squared times y cubed. Again, two exponents beside each other, you multiply them, so y to the 6th. Alright, then it says use polynomial identities to multiply each expression. A looks like it has already been broken up and is the difference of squares. Do you see how they already broke it up to a plus and a minus right here? So, it looks to me like A is 3x squared. So I'm going to write this as 3x squared to the second power. And minus B is 5y to the third, and I'm going to raise it to the second power. Now, it looks more like this should look now, but we can simplify this. What's 3 raised to the second power? What's 3 times 3? 9. X squared raised to the second power becomes x to the fourth, minus 5 squared, so 5 raised to the second power is 25, y to the 6th. Alright, this one looks like the square of a sum because it's got an addition sign raised to the second power. I know we could probably just put it in our calculator as it is, but they want us to look at these formulas. So A is 12. So I've got 12 squared plus 2. Oops, that should be 2 times 12, not just 12. So 2 times A times B plus B squared, so plus 15 squared, and we're going to simplify that by using our calculator. So 12 squared plus 2 times 12 times 15 plus 15 squared. And you should get 729. So if I would have just put this straight in my calculator, would I get the same thing? Yes, you do. So if you see this on the ACT, obviously it would be quicker to do it this way, but they're just wanting us to look at our formulas, okay? All right, now in example 3, we're going to have, before we work these 3 examples, I'm going to work 3 of our own, or that are out of the textbook. The first one we're going to look at is 9m to the 4th minus 25n to the 6th. So this is where we have to decide, is this the difference? Well, I know it's the difference because it's subtraction, right? But is this the difference of squares or the difference of cubes? So to determine whether or not it can be the difference of cubes, you take each exponent. So for instance, you take 4 and 6, and you would divide it by 3 to see if it divides out evenly. 4 divided by 3, no, it does not. So it can't be the difference of cubes. Let's see if it can be the difference of squares. Is 4 divided by 2? Yes. And 6 divided by 2? Yes. Now we need to make sure that these numbers right here are perfect squares as well. Can I take the square root of 9? Yes. Can I take the square root of 25? Yes. So this is going to be the difference of squares. So what I do first is I rewrite it where I've got 3m. If I take this and I square root it, you would have m to the second. So you divide it by 2. So 3m squared to the second power minus 5n to the third raised to the second power. The square root of 9 is 3. That's where I got 3 from. The square root of 25 is 5. That's where I got 5 from. Square root of m to the 4th is m to the second. Square root of n to the 6th is n to the third. I'm just trying to make this a little bit easier on me because I need to know what a and b are, okay? This is a, this is b. So now we write it using that difference of squares at the top. We've got a minus b times a plus b. And that would be your answer. All they want to do is for us to factor this, and that is it in factored form. B, I've got x to the third minus 216. All right, I know that this could be raised, or this could be the difference of cubes because x to the third power I know is a cube, right? But I need to make sure that 216 is a perfect cube. Well, I don't know the perfect cubes off the top of my head, but I can use this calculator. You got a math button, and then you hit 4. Math 4. Do you see how it gives us that cube root? Math 4 gives us the cube root, and we hit 216. The cube root of 216 is 6. So I rewrite this, just like I did in A, as x to the third power minus 6 to the third power. Because this tells me what A is, this tells me what B is. We're looking at the difference of cubes, so this becomes x minus 6, A minus B, times A squared plus A times B, so x times 6 is 6x, plus B squared, well, what's 6 squared? Or 6 times 6? 36. And this would be our equation in factored form. Y'all okay with that? So what we're doing is we're basically just figuring out what A and B equal so that we can simplify, or so that we can put this in factored form. And the last example out of the textbook was 11 cubed plus 5 cubed. They're both raised to the third power. There's an addition sign in between, so we're going to use the sum of cubes. So we're going to have A plus B times A squared minus A times B plus B squared. $11 plus 5 is 16, so 16 times 11 squared minus 5 times 11 plus 5 squared is 91. So 16 times 91 is 1456. All right, now let's use all that information and do these triads together. Anytime I see an even number, I'm automatically going to probably think squares, like difference of squares, sum of squares. So if I divided 8 by 2, that would leave me with m to the 4 squared. The square root of 9 is, anybody want to help me out? 3. N to the 10th, so 10 divided by 2 is 5, and we square it. So now what we do is we use A and we use B to write out our equation using to simplify our equation using that difference of squares. This becomes m to the 4th minus 3n to the 5th times m to the 4th plus 3n to the 5th. I just use that formula from the difference of squares. See an odd number in this next one, so I decide, is it divisible by 3? Is 9 divisible by 3? Yep, so it's probably going to be a difference of cube or sum of cubes, but let's double check. Math 4, 27, yes, it is a perfect cube. And 343. It's also a perfect cube. So 3x to the third raised to the third power minus 7y squared raised to the third power Remember we used this as A and this is B, right? The subtraction sign tells us it is the difference of cubes. So I've got A minus B times A squared. So what's 3 to the second power? I think somebody said it. 9. X cubed raised to the second power. So we got 2 powers. X cubed raised to the second power be x to the 6th. So that's A squared. Next we got plus A times B. Well, what's 7 times 3? 21. X cubed y squared, because you can't multiply those together, plus B squared. 7 to the second power is 49. Y squared to the second power would be y to the 4th. Now for C. That's the sum of cubes. So I'm going to have 12 plus 2 times 12 squared minus 12 times 2 plus 2 squared. Twelve plus 2 times 12 squared minus 12 times 2 plus 2 squared. You get 1736. Does everybody have everything on page 70? All right, example 4. They want us to use Pascal's triangle to expand y plus or x plus y raised to the 6th power. So the reason that we use Pascal's triangle to do this, because if we had x plus y and we multiplied it out 6 times, that could get kind of ugly, right? And take a long time. So that's the purpose of this triangle here. So I'm going to draw it out. I've got 1, 1, 1.
I need to drag Lamar to the main office, way.
Okay. So basically what I'm doing right here is I'm just rewriting out anything that we had to do yesterday. And I just need it to the 6th row. So remember this was 0, 1, 2, 3, 4. I just need it to the 6th. Alright, so a whole lot easier than you think. We are paying attention right now just to this 6th row, okay? So I'm going to start off and I'm going to write 1 times x times y. Where did I get the 1 from? The 1 came from this first term right here, okay? Where did the x, y come from? X and y right here. So next we're going to write plus 6 times x times y. Y'all see where the 6 came from? Then I'm going to write plus 15 times x times y, plus 20 times x times y, plus 15 times x times y, plus 6 times x times y, plus 1 times x times y. This is where it gets even easier. We start at the first x. We're going to raise it to the 6th power. The second x is going to be raised to the 5th power. Third x is going to be raised to the 4th. Y'all see what I'm doing here? All the way down to 0. We're going to do the same thing with y, except we're going to start with 0. 0, 1, 2, 3, 4, 5, and 6. Now we can clean this thing up a little bit. Not much to clean up here. We can just get rid of anything raised to the 0 power, because anything raised to the 0 power is always 1, okay? I'm going to cross it out. And 1 times x to the 6th is just x to the 6th. Would y'all agree? Plus 6x to the 5th y. Do I need to write the first power? No. Plus 15x to the 4th y squared. Plus 20 x cubed y cubed. Plus 15 x squared y to the 4th. Plus 6xy to the 5th. Plus y to the 6th. That canceled out there. It got blurry on me. So had we taken our time out and actually distributed everything, it would have been a little more complicated, right? Instead, we were able to do it using 2 lines there. Alright, now they want us to use that binomial theorem, or the Pascal triangle, to expand out these next 2 examples, and then we'll be finished. But this one needs us to raise it to the 7th row, or use the 7th power, so I'm going to go up here where I'd already started, and just finish this one out. Because the next one's to the 6th, so the 7th is all we'll need to go to. Alright, this one can take up a nice amount of room. It did for me on my page anyway. So I am going to start like over here in my margin so I can go all the way across, okay? So we're using the 7th row. We're still going to use these 2 terms on the inside. So I've got 1 times x times negative 1 plus 7 times x times negative 1 plus 21 times x times negative 1 plus 35 times x times negative 1 plus 35 times x times negative 1 plus 21 times x times negative 1. Are y'all seeing where I'm getting these numbers from? Are you sure? Everybody cool with that? Plus 7 times x times negative 1 plus 1 times x. Whoops, I didn't mean to put parentheses. It'll be right. Times negative 1. Alright, this time when I'm looking at my first variable or my first term here, what exponent am I going to start with? Start with a 7. 7, 6, 5. Oops, I said 5 and wrote 4. 5, 4, 3, 2, 1, and 0. So if we start right here, we have 7, 6, 5, 4, 3. Whoa, I missed one. 3, 2, 1, 0. Now we got to simplify this bad boy. Alright, remember I told you anything raised to the 0 power we can automatically cross out, right? So now I've still got 1 times x to the 7th plus 7x to the 6th. Well, let's see. Negative 1 raised to the first power is negative 1. Y'all see that? So times a negative 1 plus 21x to the 5th. Negative 1 raised to the second power is positive 1 plus 35 x to the 4th times negative 1 plus 35 x to the 3rd times positive 1 plus 21 times x squared times negative 1 plus 7 times x times positive 1 plus 1 times negative 1. So if it was an even exponent, and you could have put all these in your calculator, if it was an even exponent, it became a positive 1. If it was an odd exponent, it stayed a negative 1, okay? So now we go through and simplify. 1 times x to the 7th is just x to the 7th. 7 times negative 1 is negative 7, x to the 6th. 21 times positive 1 is a positive 21, x to the 5th. 35 times negative 1 is a negative 35, x to the 4th. 35 times 1 is a positive 35, x to the 3rd. Minus 21x squared plus 7x minus 1. So that right here would be your final answer. I'm going to do the same thing with the second one. I'm going to start it out here so that I have enough room. But what row are we going to be using for this part B? The 6th row. So I've got 1 times 2c times d plus 6 times 2c times d plus 15 times 2c times d plus 20 times 2c times d plus 15 times 2c times d plus 6 times 2c times d plus 1 times 2c times d. Somebody open the door for me, please. Alright, now we're going to go through and put our exponents with it. We got 6, 5, 4, 3, 2, 1, 0, 6. Oh, that went off. That should be a 6. 5, 4, 3, 2, 1, 0. Anything raised to 0 power, I go ahead and cancel out. Now I need to simplify. I don't know what 2 raised to the 6th power is. 2 raised to the 6th is 64. So now I've got 1 times 64c to the 6th plus 6 times 32c to the 5th times d plus 15 times 16c to the 4th d squared plus 20 times 8c to the 3rd d to the 3rd plus 15 4c squared d to the 4th plus 6 2c times d to the 5th plus 1 times d to the 6th. Simplify this thing. 1 times 64 is just 64 c to the 6th plus 60 or 6 times 32 is 192 c to the 5th d plus 15 times 16 240 c to the 4th d squared plus 160 c to the 3rd d to the 3rd plus 60 d squared or c squared d to the 4th c squared d to the 4th plus 12c d to the 4th, fifth, plus d to the 6th. I'm writing what I want you to do for practice problems is going to be on the next page. You should be able to do numbers. Should be able to do all of them. Shouldn't be too hard for you.